Okay. The core of probability theory is to calculate the probability of an event to occur in a random experiment. Okay, so we will take an angle to look at how probability is assigned to an event in a sigma algebra. Okay, so we will from the angle of the perspective point of view. Okay, so we will see that. So given a mathematical model of running experiences up to now, that which we have a sample space X and a collection of events of interest, which will be a sigma algebra, because we like logical structures is embedded in such a collection. Okay, so that's we have a sigma algebra F. Okay, and so we recall here that a sigma algebra is a well-structured collection of events, okay, of interest. Right? So with some space, sigma algebra, then the assignment of probability to events in the sigma algebra F, i.e. a mapping we call P, okay, from the sigma F to the set of all real numbers, okay, should satisfy the following three we call intuitive axioms. Okay, so I will list these three axioms. Axiom number one is that we call non-negative, so we call non-negativity axiom, which says that the probability to assign to an event E should be non-negative. Okay, so probability always non-negative for all events in the sigma algebra F. Now the second axiom we call normalization. Okay. the probability of the total event is equal to 1, which sometimes we call 100%. Okay? Right, this is about, so the first two axioms is quite intuitive, right? So we all accept these two axioms. The third axiom is a little bit technical. We call countable additivity. Countable theory states that for any sequence of mutually exclusive events E1, E2, etc. The meaning of mutually exclusive events says that EI intersects EJ is the empty set. So they are exclusive to each other, which means that they are disjoint from each other. Okay, for I not equal to J. Okay, so for such a sequence of mutually exclusive events, the probability of their union okay, or sometimes we just say that and we put a dot here, and I will explain what the meaning of the dot union. Okay, so the union must be the sum of the probability of each event E sub n. Here, the symbol dot union means the disjoint union operator, and we said A disjoint union B means the union of two disjoint sets A and B. So whenever we see this disjoint union, we mean that all these events are disjoint from each other. Okay, and then we take the union. Okay, so indeed, disjoint union is a kind of union, but say some other things, which is that the events, okay, joined in this union will be mutually exclusive. Okay, so for mutually exclusive events, we understand that they cannot occur simultaneously. Okay, they cannot occur simultaneously, so that the probability of their union, okay, should be the summation of the probability of each event E sub n. Okay, so this is also quite intuitive. Okay. Yes, please.
So the dot means that it is mutually exclusive.
Yeah, that's the meaning, yes. So all the set in this union are disjoint from each other. Yep. So this symbol sometimes simplify our notation. Okay, so okay. So any questions about these three axioms, about the requirements needed when we assign probability to events? Yes, please.
What is that mapping F to R? R is the real
R makes the set of all real numbers, because probability is a numerical value, right? It's not categorical value. It's not A, B, C, D, E, F, G. It's just a numerical value. So it should be a real number. And but axiom number one says that it should be a non-negative real number. Okay. All right. So, and I specifically include a non-negativity into the axioms because that would be more convenient. Okay. To put it as axiom number one. Okay. So probability is actually a function, okay, from the signal algebra to the set of all real numbers. Okay, and so now a function P from the sigma algebra to R, okay, which satisfy the above three axioms, okay, is called a probability function. Or a probability measure on the sigma algebra F. Okay. Okay, so even though you have the same sample space, the same sigma algebra, they may have different probability function. Depends on how you execute the running experiments. Okay. For example, last Tuesday I showed how to flipping two coins, right? And in general, that's for the central government, that when they make the coins, they make every coin fair. Okay, so if you flip one coin, the two faces will appear equally probable, right? This is the common situation. Okay, and so in that kind of coins, when you want to assign the probability to events, then we will say that you should abide to the fairness of the coins. But in gambling societies, some gambler, if the game of the gambler involving flipping coins, some gambler may make unfair coins, right? It's possible, you don't know, but they usually want to cheat on the customers. Okay, so when the gambler executes the flipping coins, then the probability for each event may be quite different from that under the fairness condition. Okay, so if you use fair coins, then you will build up a probability function. That's good. But if you use unfair coins, then the probability function you accept will be quite different. Yeah, and we will see that later on, maybe in the exercise. Okay, so it's possible for a given sample space and a given sigma algebra, we may have different probability function established depending on how you execute your random experiments. Okay. All right, so that you should know the concept that anyway, probability is assigned according to the nature of the random experiments. And you have to know how the probability is assigned. Means that you have to establish the probability function before you can answer questions about the probability of a certain event to occur. Is that okay? Good. All right. So this week we'll talk about the very, very fundamental concepts in probability theory. Everything will be grown up from these fundamental concepts. Okay? So every time in this semester, you have to go back to this material. Refresh yourself, and to thinking about that, and you will gradually understand why they are so important to establish the mathematical model, including a sample space, signal algebra, and the probability function. Okay. Okay. So I would like to deduce several propositions from the three axioms. So the first one is proposition. (2.3.a). All right, so for a probability function, the probability of the empty set is equal to 0. This is compared to axiom number 2, the normalization. For any probability function, the probability of the total event must be equal to 1. Okay? So, on contrary, the probability of the empty event or the null event should be equal to 0. Okay? And now we see how we prove this fact from the three axioms. Okay. So now in this case, we let E sub I to be the empty set for I equal to 1, 2, 3, etc. So we consider a sequence of empty or a sequence of null events. So every event is just the null event. Alright, so in this case, then of course, their intersection must be the empty set. So they are mutually exclusive, specifically, right? So this is how I consider they are mutually exclusive. Okay? And now we can apply axiom number 3. Because now we have a sequence of mutually exclusive events. Right? Because this is a constructed sequence of mutually exclusive events. So by axiom number 3, we know that the disjoint union is the summation. Okay, so we have this identity, and that is the summation of the probability of. And specifically, maybe I will write it down here. Okay. Now, since the disjoint union of E sub I is just the disjoint union of the empty set, because events empty set. So this is, of course, is empty set there. Okay, so we have that the probability of the empty set is equal to the summation of the probability of the empty set. Okay. Now, by axiom number 1, we know that the probability always non-negative. Okay, so so there are two cases. If the probability of the null event, which we call C, is greater than 0, so if it's positive, then what happened? C is equal to summation and C. Now, you sum the C for infinitely many times. So why is that? This is infinity, right? If C is any positive number, no matter how small it is, right? Maybe C will be 10 to minus 100. It's very, very small positive number. But if you add them infinitely many times, then the result should be infinity. And C is infinity, which is a contradiction. So you see, if this probability C is positive, you get a contradiction. So the only choice is that, well, so we conclude that because from axiom number 1, probability always non-negative. So the only possibility is that the probability is 0. Okay, so we deduce this result from axiom number 1 and axiom number 3. Any questions? Yes?
Explain the line with since, after since.
This union is empty set, right? So this is empty set.
Right.
So P empty set is equal to summation of P of empty set. Okay.
What is, we have taken P of phi equals 0, right?
Yeah, so suppose that P of the empty set is a number which is greater than 0. So suppose it's C, right?
Is the assumption that
Yeah, because there are only two possibilities, right? Either equal to 0 or is positive. Only two cases. Now we first consider that if this quantity C is positive, when E is positive, then I put substitution to here, right? To this identity, you get C equal to this is summation. But this summation is infinity. So you get a contradiction.
So P should vary from, P should be in the above line. Yeah, P should vary from I to infinity.
Yeah, here, because you have, okay, you have infinitely many terms to add together, right? Here. And each one, because E sub I is empty set, right? By our construction. Okay, so I put them so here, so that every terms in this series sum are the same. They are the same, right? And this is the same number here. Yeah, so the key would be here, and we also know this union is at the empty set. Because this construction is very specific. Yeah. Because I want to apply axiom number 3. And axiom number 3 is true for any sequence of mutually exclusive events. There are a lot, right? Actually, infinitely many sequence of mutually exclusive events you can construct. Okay, so this is one of the construction. For my purpose, right, I want to give you a proof, which is very fundamental. Okay, so everything I give to you started from very near to the earth, right? And very grounded. There's no any advanced concept at all right now, right? Everything just come in something, right? Add something, many things, yeah. Okay, so this is for you to learn how to give a proof, okay? Because it depends on this specific sequence of mutually exclusive event I constructed, right? And then you just do the proper reasoning. Questions? Okay, so if no further questions, okay, the second one is called finite additivity. Right. Finite additivity is a specific version of axiom number 3, and it is very useful, right, in many computations. Now, for any finite sequence of mutually exclusive events E1, E2, up to En. So we have a finite sequence of events here. All right, so which means that they are disjoint to each other. Now, then the probability of their disjoint union is equal to the summation of individual probability. Yeah. So you compare that, this proposition to axiom number 3, you see now we can consider only finite number of events here. Okay, so it's called finite additivity. All right, and the proof here, because we want to use axiom number 3, and axiom number 3 is about sequence of mutually exclusive event, infinite sequence here, right? E1, E2, E3, etc. But now we have only a finite number of events in the sequence. So how to build up an infinite sequence? And we still want there to be mutually exclusive. How? Okay. So we will append more events. Actually, a good choice is to append more events. So we let E sub I to be the empty set, okay, for all I starting from n plus 1 and plus 2, etc. Okay? So now we establish an infinite sequence of mutually exclusive events. Because each E sub I is an empty set. So, for example, U1 intersect empty set is still empty set. Okay. So now EI, okay, is a sequence of mutually exclusive events. in F. Okay? So by axiom number 3, okay, so the union, the disjoint union has probability which is equal to the sum of the probability of each E sub I for I from 1 to infinity. Okay, this way. All right, and now we specifically we split this series sum into 2 parts. Right? The first part is about the summation of the probability of the first n events in the sequence. And the second part, starting from I from n plus 1 to infinity and p sub I here. Okay? So we split the series sum into 2 sums. And by our construction, when I starting from n plus 1, each E sub I is the empty set. And we have shown in the previous proposition, the probability of the null event is equal to 0. Okay, so here we have zero here. So this is by proposition 2.3.8. This is 0. And the summation of 0 will be 0. Okay, so this is equal to. So the series sum becomes to a finite sum first. Now, since okay, now the union here, okay, is actually equal to the finite union because the EI for I greater than or equal to n plus 1, they are all the empty sets. So you add nothing at all. Okay. All right. So you have this one. Okay. So that this is the. So we have. Okay. What we want. Okay. So to prove the second proposition, we need the first proposition as well as the axiom number 3. Yes, please.
On the first one, it's a contradiction because C should have been 1.
No, because C is a positive number, right? It's some specific, so it's a finite number.
Oh, it has to be finite.
Because it's a real number. Every real number is a finite number, right?
Also, why did we assume it to be greater than 0? Because, the probability of happening like this.
Yeah, but axiom number 1 is always non-negative. So there are only 2 possible choices. One choice is that it's equal to 0, or it is positive. And I want to eliminate the second choice. So if I assume that it is positive, Because C is a specific real number. Python.
Do we need to prove this? It's intuitive that it's always going to be 0.
Well, intuitively, yes, it's 0, right? But how do you know that? You know, it's always difficult to prove the more fundamental things, right? Okay, you have to choose something, right? We have choose the 3 axioms here. This is intuition, right? Because we want the total event to be 100%. You choose that. So you don't want to prove it, right? This is your choice. You should choose something as the starting point. And it's better. So it's just, if you have experience of, that's just, I mentioned about the Euclidean geometry. Euclid developed the Euclidean geometry more than 2,000 years ago, right? In Greece. Okay. All right, long time ago. And at that time, scholars faced the challenge how to select some statement which we think we can't prove it. Because there are a lot of intuitive concepts, okay? But if you say that everything is just intuitive, well, then that becomes to be a big mess later on, okay? Even though I know in Taiwan, especially in the middle high school, students are taught by intuitive Euclidean geometries. Like, for example, there are quite a few theorems about the equivalence of triangles, and they should be proved, but they use some kind of they do some experiments, right? They draw something and compare things together. Say, okay, if you have triangles and if the corresponding sides are equal to each other, then they are equivalent to each other, right? This is very intuitive reasoning. But in the original Euclidean geometry, this should be a theorem and can be deduced or proved by axioms. Euclid selected before. Okay? So this kind of deductive reasoning is quite often in mathematics. If you recall, I believe you took linear algebra last semester, and you learned the concept of vector spaces, and there are quite a few axioms, okay, for vectors to become to be vector spaces, and you deduce a lot of things, including dimensions, basis, linear independence. A lot of concepts can be built from that axioms, okay? And if you look at all these axioms, they are very simple axioms and really intuitive, okay? And the reason why we want to select a set of statements as axioms is because I want to identify if in later on, maybe in your engineering problems or other mathematical problems or economic problem or financial problems, that you identify an algebraic structure and find that it is a vector space. Then you can apply linearity, the whole theory to your construction. And how to identify an algebraic object to be a vector space? Well, you just check all the axioms of this list. And if the axioms are satisfied, then you can say, okay, this vector addition, scale multiplication together, if you define, right, then you can apply all the results in linear algebra to that algebraic object. This is the same because we need to construct the probability measure. And how do you know the probability assignment is a probability function? Well, you check the probability assignment, whether they satisfy these three axioms. The first two are quite simple, but the third one is sometimes challenging. Okay, sometimes challenging. But still, these three axioms is still a good choice. Okay, because that for more than 100 years, that the mathematicians satisfy these three axioms. Okay, they think that this is a good choice. So now we are in the 21st century already, and I believe later on, maybe in a little, suppose human being is able to sustain for more than 1,000 years. If human being do not destroy the environment of the earth, okay, we still can live in this planet. But I believe that the three axioms is still a good choice. Yeah. Even though I cannot predict the future. Yes, please.
It's like the same that we study in linear algebra, the 8 properties of vector space.
Mm-hmm.
If something follows those 8 properties, it can be called as vector space.
Yeah, and now we will see, we call a probability space, including 3 elements: sample space, sigma algebra, and a probability function. So every random experiment is corresponding to a probability space. And once you establish a probability space, then you are able to answer any questions about the particular random experiments, including the core task to answer, to calculate the probability of an event you are interested in. Okay, so this section is to establish the third element of the probability space. Okay, the probability function, because we already know from the previous section about the sample space and the sigma algebra. Okay, so now we're facing probability functions here. All right, so the second proposition is finite additivity. We have. Right? And the third proposition is that for any event in the sigma algebra, its probability assignment would be between 0 and 1. Okay, this is very intuitive, right? Very simple fact. Right? But we still have to prove it. Why everything should be proved from the 3 axioms? Okay, just like we had done in Euclidean geometry or in the vector space. All right, so since E and the E complement should be disjoint, of course. And when you take the union, they should be equal to the total event. Okay, so we have that. All right. So that's the probability. So we have 1 is equal to P of X. So this is axiom number 2. And so this is proposition. This is finite additivity. Okay. Finite additivity is just proposition 2.3.b. Alright, so this is axiom number 2. Okay, and you have that. So 1 is equal to this sum. Okay, now, so that So that PE is equal to 1 minus PE complement. All right? Now, this is from axiom number 1. Okay? And this is less than or equal to 1. Since PE C is greater than or equal to 0 by axiom number 2. And this is the end of proof. All right? So I will use this kind of method to simplify my proof. Okay. So I hope you understand that this means that the reason I give to you this inequality. Okay. It's okay? So because this one is non-negative, so if 1 minus something which is non-negative should be less than 1. Yeah. Okay, so this is the third proposition we have. Okay, so now we have we check 2 examples. This one is about flipping 2 coins. Oh, okay, yes, please.
How did we write the last probability of E?
Because this is the joint union of 2 events. So by the final additivity, n is equal to 2, right?
There's nothing common in these two, so that's why we can write it separately.
This one?
Yeah, so E intersection E complement, so they don't have anything in common.
Yes, because so I put the joint union. Yeah. So I have 2 events, they are disjoint to each other.
So their probabilities can be written separately.
Yes. Yeah, because that's just like here. Suppose this is a sample space. This is E, is C here. Yeah. And so, so these 2 events are disjoint to each other. Yes. So by the finite additivity, we know that this disjoint union has probability which is equal to the sum of these 2 events individually. Yes. And this is a special case of finite additivity here. Because here we consider arbitrary n events. N can be 2, 3, 5, 6, 100, 1,000, a million, right? And this is just a special case for n equal to 2. Okay. Very good. You track very well. Okay. So now we apply to our example. So in this random experiments, right? We have shown that the sample space can be represented by it's a set of pairs. Okay, right? So it consists of 4 possible outcomes. Okay, so we have 4 possible outcomes here, and the sigma algebra we select is the power set of this, right? In previous section. Now, the probability assignment can be like for every singleton, a singleton here is just a set consists of only 1 element. All right, so this is 1/4. Okay, so the events the event that some specific outcome occur, right? And so we think that the outcome, this four outcome occur with equal probability. Okay, this is very common, means that we are considering fair coins. Okay, so the basic things here, once we make such a probability assignment, so this probability assignment reflecting fair coins. Okay? So we understand that we use fair coins to do these learning experiments. Because we set two coins, we don't know what's the quality of the coins, right? You have still variation about the quality of coins. But if you use fair coins, then these four possible outcomes, each of them should occur with equal probability. So we call that they are equal probable outcomes. And so we have the assignment here. So that's with that. So that the probability under this assignment, the probability of an event is equal to, we count how many all right. So if we have a probability function, P with these properties, all right. So that's I should say any probability function P satisfying given the above assignment, above probability assignment, to singletons, right? Should have here and the reason here is because E is the disjoint union. Okay. For example, if E is equals to, right? This is the event that there are only one head appears in the outcome. Only one and only one head appears in the outcome. So that E is the union of these two singletons. Because E has two elements, right? So E consists of two outcomes. And so E is here, okay? So that this is actually okay, so I hope that we understand that This is the dot union. So you take every outcome in the event and the union their singletons. Okay. So this is the disjoint union. So by the finite additivity, you know the probability of this event is equal to this finite sum. Okay, and we know that for each singleton, the probability is equal to 1 over the size of the sample space. Okay, and so you get, so this is the counting, about the countings we have. Okay, so any probability function, okay, and so the question is, do we have one such probability functions given the above probability assignment? Which means that, do we have a probability functions satisfying the three axioms? Okay. Okay. So we will show in section 2.5 that there is a unique probability function satisfying the probability function, probability assignment above. Okay. So this is quite a useful method to construct a probability function. You assign probability to some fundamental events. Okay. For here, every singleton is a kind of fundamental event. Okay. We will define that later on. And for fairness, for fair coins, then this is very reasonable that the probability for each singleton is just 1 over the size of the sample space. Okay. Right. And then we can use the finite additivity, okay, to, if we have a probability function, okay, given the above probability assignment. So now, if we have such a probability, and the probability function should satisfy the three axioms and the three propositions we proved here, okay, including the finite additivity. Okay, so that because every event is the disjoint union of singletons, okay, so that the probability of the event is equal to summation of the probability of every singleton for every sample in this event. Okay. Okay. So with this identity, so now we know the probability of an event is actually the size of the event divided by the size of the sample space. Okay. All right, so this, so we will go back to this kind of problem in section number 5. Any questions about this simple example? Okay, so we take a break up to 2:30. Yes. 结算 Okay. Okay, I think it would be a proper time to illustrate how about unfair coins are used in doing flipping to coins. All right, suppose that a gambler make up a coin, right? So I try my best, okay? The coins. All right. So this, so there are two layers. There are two layers. So this is the up face. Okay. So the layer tending to the up face made by aluminum. Okay. And up to the down face made up by the iron. Okay. And we know irons has high density than the aluminum. Okay, so if you make up such a coin, you flip them, the probability you get, so that you get head. So this shape, you say this is head face. Okay, all right. So that would be 1/3 only, because it tends to has the iron in the bottom, right? Because the iron is heavier, okay? And so the tail, I'm sorry. Okay. So the tail with the iron, right? So this has fewer probability to have. Yeah?
So I read this example in the book. I don't understand that why the probability became 3. Like the sample space became 3.
The sample, no. I just say, so, no. Okay, so that, I know that, in your questions. So the probability of the head will be, okay, because to flipping to coin is just like a two independent flip of one individual coins. Okay, so that the assignment. Good question. So this will be 4 9s instead of 1/4 right now. And the probability to have head and tail will be, and the 2 9s, probability to have tail and head. So this is the assignment to each singleton. Okay, each singleton for unfair coins here. And so if the running experiment is to do 31 coins, so that is the head and tail only, right? Okay. Right. So this is our reflection about using unfair coins. And once again, with this assignment, then we can show there is one and only one probability function satisfying these 4 assignments. So now here that so the probability of the event, becomes to be okay. So this is the best we can write here. Okay, because here this is a simple, so we have this simple expression. Okay, but for the probability assignment, okay, and also okay. Okay, sorry. Okay, so if the metals make up the coins different in different structures, then the probability will be changed. Okay. So anyway, so different random experiments, even though that they seems to be the same, but if you use different use coins with different qualities, then the probability assignment will be different. Okay, so with the same sum space, the same sigma algebra, okay, you may have a different probability assignment. Actually, you have infinitely many probability assignment, right? Any questions about this example? No, good. So now we will take a second example. We're measuring the lifetime of a light bulb in working hours. Okay, now in this random experiment, we know the sample space is just the set of all non-negative numbers, okay? And the sigma algebra we select is the Borel sigma algebra the sample space, okay, and we have defined a Borel sigma algebra which is the smallest sigma algebra containing all subintervals of this infinite interval from 0, okay, to infinity. So this is the sigma algebra we select, the Borel sigma algebra. Now, how do we construct a probability function? Because you know, the outcomes is non-negative real numbers, so they are uncountable many non-negative real numbers, right? Because you have continuum, right, in this interval. So the nature of this learning experience is quite different from the previous one, because this is the discrete type, and indeed is a finite problem. But this is actually more complicated problems. Okay, so I will demonstrate a common way to establish a probability function. The way is that we select from the experiment from doing quite a few experiments, right? So let fx be a non-negative valued Riemann integrable function. For example, a non-negative valued continuous functions okay, on the sample space or on this infinite interval such that the improper integral, right? So this is the integral of the function over the whole interval is equal to 1. Okay. All right. So suppose we have such a non-negative valued Riemann integrable function, because we will do the Riemann integral here. Okay. Okay. And quite often that the f of x is just a continuous function, okay, on this infinite interval. Okay, quite many. But some of the possibility is that f of x may have a finite number of discontinuity. It's quite often to have such kind of functions. Okay, so there are many choices. Okay, and suppose we choose one. Okay, is this property there? Now, the central, the most important event will be subintervals of this infinite interval, right? Because when we construct the sigma algebra, we want a small list sigma algebra containing all subintervals. Okay, so subintervals are the importance events we want to investigate. Okay, and okay, and so from 0, right here. So the f of x, for example, x minus x here. This is one of the example. Okay, and so this function, you see, is continuous. So, and if we do the integration, we find What is that? This is equal to 1. This is equal to 1 here. So that e to the minus x is a good choice here. Okay? So that is a non-negative value there, because exponential function always non-negative. Actually, it's positive, but at this stage it's non-negative value there. Okay, and it's continuous, so that it's Riemann integrable. Okay, over this one, because the total integral here is equal to 1. Okay. All right. So it's a good choice. And then for finite intervals, the probability of the open interval is equal to the probability of the closed interval is equal to the probability of the half open, half closed. All this probability is defined to be okay. So this is our assignment of probability for these 4 kinds of finite intervals. Okay. So specifically, the probability so that the area is used to assign as a probability of this open interval, so that okay. Right, now it can be shown that there is one and only one probability function P on the Barrera sigma algebra on the semi-infinite interval, which satisfy, suppose this is 2.1, 2.1. So that the probability that an event E occurs will be denoted as for all event in the Barrera sigma algebra. So in particular, this assignment, we define all these probabilities are the same, okay, and they define to be distributive integral. So this is the probability assignment, right? We like to have, okay. And then later on, you will see that the f of x is actually called the probability density function, okay. The probability density function that we select. So if the light bulb, you know, if you go to the supermarket, they are different manufacturer, right? For the same type of light bulb. For example, you want to buy 60 watts light bulb, right? There are many different makers, okay? And different makers have their own probability density function about the lifetime. Okay, Philips is one of the famous makers you have. Okay, and of course you have other makers that you go to shopping around a supermarket. Okay, so every factory has their own probability density function f of x. Okay, maybe they keep as a secret. We don't know them. Okay, and so they will have the ability to establish, because using the probability density function they have, then they usually do this kind of probability assignment. Okay, so they know that if they make a light bulb, the lifetime of that light bulb has lifetime in between A and B. All right, they can calculate the probability as their quality control. Okay, so every year or maybe every season, the manufacturing will try to estimate their probability density function. They should find out the probability function. And the way to estimate a probability function we will call statistics. Okay, so we use statistical method to estimate the probability density function f of x. But in probability theory, we take a probability density function for granted as the starting point. As the starting point, okay? So, right. So you may be curious about how do we select a probability density function, okay? So that I have made a remark. F of x is called a probability density function. On this semi-infinite interval, okay? So it's called the probability density function because it's just like a density, okay? Because you have to integrate over the density function to give you the probability. Just like the mass density function, if you consider a wire, okay, and the wire has the mass density, okay, and so if you want to know in a section of the wire what is their mass, then you should integrate, all right, over the mass density function as you learn in physics. And here we just give you the probability density function here. So with the probability density function at hand, then you can assign the probability to each subinterval of the semi-infinite interval from 0 to infinity, like this one. And it can be shown, but I will not do the proof in this course because this is more advanced. So I just tell you that indeed in mathematics we can show that there is one and only one probability functions which satisfy this assignment, one and only one. So it's unique. Okay. Okay. And so with this assertion, you know how to establish probability functions for random experiments with continuous outcomes, like this one. Okay. Many problems is pretty much like this kind of random experiments. Okay. So you will do that, and once you know there is one and only one probability function, okay, given these probabilities, then you are able to use all the properties of a probability function to deal with your problem. Okay. Any questions? So every time when we write integral in this way, you know it's about a probability of certain event, okay? And this is just the integral you learn, the Riemann integral you learn in calculus, okay? In calculus. So, and by our definition, there are probabilities of different events because these four events are different. But they have the same probability, okay? Because we are using a probability density function. So you integrate a probability over 1 point, the result is 0, right? All right, so it doesn't matter whether you include endpoints or not. Okay. All right. Right. So there are some simple properties about probability function. So let's say some simple propositions. All right. So in this section, EF, E1, E2, up to En are events in a sigma algebra F on a sample space S. And P is a probability measure. Of function, okay? I often call probability function on F. All right, so proposition 2.4.1. So 1, 2, 3, 4 are propositions corresponding to the proposition provided in the textbook. But if I number them by A, B, C, D, which means are extra propositions, okay, I give in the lecture. Now, the complement of E has probability, which is equal to 1 minus the probability of E. Okay, and we found a similar proof in a previous proposition. All right, since the total events is the disjoint union of E and its complement. Okay, so we have okay, and so again, this is XM number 2, and this is the finite additivity. Okay, so this is implies that PE complement is equal to 1 over PE. Okay, so the proof is quite simple. The second proposition, second simple proposition, 2.4.2. If event E is a subset of event F, then which means that event F is bigger than event E, then the probability of event F is bigger than the probability of event F. Okay. Now, so our situation is here. So this is F. Okay, and this is E. All right. So that this is F minus E. And we have some space here. All right. Okay, so the proof quite similar to that. Since okay, F is equal to, since E is a subset of F, F actually is E, disjoint union of F minus E. Okay, so this is implies that probability of F, okay, is equal to probability of E plus probability of F minus E. By finite additivity. So this is implies that. So this is finite additivity. And because any probability is non-negative, so that PE is less than the PF. So this is the XM number 1, which is implies that because P okay, so P of X is the addition of two non-negative numbers, and because this one is non-negative, so P of X is greater than or equal to P of E. Okay. Right. So you see that these two propositions are quite simple. Yes, please.
This the one and that you were just erasing, is it the same? This one and this is same?
You mean for the first position?
This and
Yeah. Yeah, it's about the complement. You mean this way? Because this is okay. If this big box is the summer space, and this big circle is the event F. Then outside of event F, give you F complement. So every time when we write F complement, we mean X minus F. So you use the total event to do the set minus. Okay. But if it's this one, this is in general, right? So this is not equal to F complement. This is not equal to E complement, no. Different, okay? Because it's F minus E.
Right, because E complement would mean all the green in that area.
E complement means including that and also here, this part. Okay. So that you have to understand that. Okay. So this is E. Okay, different. Great. So now, proposition 2.4.3. It says that what if we want to compute the probability of the union of E and F, and this union may not be disjoint union, because if it's a disjoint union, then you can apply the finite additivity. Okay, but in general, it's not a disjoint union, just a general union, and so this probability actually is the addition of these two individual probability minus the probability of their intersection. Okay, so the situation is here. So this is the sample space. So this is E, F, and you have E intersect F here. And so this part would be E minus F, and this part is F minus E here. Is that okay? Okay, so the proof, right, since E union F, because we want to apply finite additivity, so the E and F, we will, so that the union of E and F will be, okay, I count you near to the speakers. So there are three parts: E minus F, disjoint union, F minus E, and disjoint union, E intersect F. Is that okay? From the Venn diagram, so the union of E and F consists of three disjoint parts. The first part is here. The second part is here, okay? So you can see okay. And here. So there are three parts. Okay, you have disjoint union. So that by finite additivity. Okay? Now also, since we know E is equal to E minus F union E intersect F, so disjoint union here, and for F, it's F minus E disjoint union E intersect F. Okay. So that probability of E is equal to probability of E minus F plus probability of E intersect F. And probability F is equal to probability of F minus E plus probability of E intersect F. Again, by finite additivity. Okay, so this is implies that PE minus F is equal to P of E minus P of E intersect F. And P of F minus E is equal to P of F minus P of E intersect F. Okay, so this expression will go to here, and this expression go to there. Okay, so now and you cancel one. So finally, you have so you get this is the result. And the subproposition can be extended. Right, and when we do a extension, it will be called inclusion-exclusion identity. Okay, this is quite useful. It's give you the probability of the union of a finite number of events. The third proposition about the union of two events, but here we deal with a finite number of events. This is the general case, and so this is will be you sum over all probability I, but it's too much, right? So the inclusion because it's too much, so you have to subtract their intersections. Okay, so you have to subtract their intersections, but this will be too much, the subtraction too much, so you have to add back the intersection of three of them. Okay, so okay. So in general, you have to add our subject, the intersection of all of these events, of n events. So that would be and the final one would be n plus 1 And there is only one possibility for the intersection of the n events. Okay, so inclusion, exclusion, inclusion, exclusion, inclusion, exclusion, alternatively. So that's why it's called inclusion, exclusion, identity, or principle. And we put it in a summation, so that will be okay. And so the proof, it's by induction on n, and I have put it as an exercise. Okay, for n equal to 2 has been proved in the previous proposition. Okay, so you start with n equal to 2, right? You know that, and you can assume that it's good for n. Then you prove for n plus 1, this is also true. Okay, so this is the method of induction. All right, so I ask you to do it. Okay.
So we take the first one as the base one?
Yeah, the base one, because we have already done for n equal to 2. For n equal to 1 is simple, right? 1 is simple. And 2 is a little bit complicated, but it's still simple, right? We have already proved. And so the induction steps is that we assume this formula is true for n. Then you prove if n becomes to n plus 1. Do we have the same formula, similar formula? Okay. Or you can say, when n equal to k is true, how about n equal to k plus 1? Yeah. So this is the induction. Okay. So this is the exercise for you to do. Okay. If you have questions, you can ask TA next Monday. Okay. I have to stop here. Okay. And the recommended homework is a bit bigger than what I have told up to now, because I include part of the section 2.5, because 2.5 is very simple. It's about the nature of the problem is 2.5 is about the first example about the equal probable outcomes. Okay, so they are simple, but all right. So so I will do some more in section 2.5. Okay, next week. Okay, questions? No. Good. So I'll see you next Tuesday.